Hey, welcome back to another lesson in AP Calculus. This is lesson 4 of Unit 9. Unit 9 has been all about slope fields and solving differential equations. We're going to finish off by looking at some applications. For these problems here, we will occasionally use a calculator just to help us find some kind of yucky answers, get some decimal approximations so we can maybe better understand what's going on, but it's important that we do not use a calculator to actually solve the differential equation. And that's because the technique of solving a differential equation is almost exclusively on the non-calculator portion, since some calculators, such as like the TI-89, can solve a differential equation. And most others cannot. So that's why they're, to keep it fair, they're usually on the non-calculator. So we want to make sure we're practicing this without any aid we wouldn't have normally. So the rate of change of the number of bears, n of t, is directly proportional to 1200 minus n of t, where t is the time in years. So in this problem here, we're told that the rate of change of some function is proportional to the function's value itself. I don't mean the rate of change is n of t. I'm saying the rate of change would be n prime of t. Okay, n of t is the number of bears, and the rate of change of that number of bears, that rate of change in the population, is proportional to 1200 minus n of t. And in problems like this, you're typically going to be given a couple of different pieces of information because we're going to have a couple of different unknowns. When t equals 0, the population is 300, is our first piece of information. And then it'll say if n of 4 equals 600, find n of 8, and the limit as n goes to infinity. All right, let's get right to it. So the rate of change in the number of bears, I can call that n prime. I'm going to call it dn dt. Is directly proportional. A direct proportion means you have some constant of proportionality k times that value. So the rate of change is somehow proportional to this. And then instead of saying n of t, I'll just say n. All right, well, we can solve this as a separable differential equation. I'll simply divide both sides by 1200 minus n. And then I get k dt. Now I can integrate both sides, and this gives me the natural log of the absolute value of 1200 minus n is equal to k t, because k is just some number, so when I integrate k, I get kt plus some constant c. I will now exponentiate both sides, and it's important to use the technique we practiced in lesson 3. That the exponentiating will cancel the natural log, but I'm also going to be able to remove the absolute value because I'll be able to bring the c down in front, because this becomes e to the kt times e to the c. Since if we wrote it, we could write it like that, since when you have the same base, you would add the exponents and get back e to the kt plus c. But I'll just put the big C out in front there and make it CE to the KT. All right, I will subtract 1200 over to the other side and divide by a negative 1. If you don't mind, I'd like to do that all in one step. So negative C is just C. And then this becomes plus 1200. And there we have it. All right, so now we've got a couple different unknowns. We've got an unknown constant c, and we've got an unknown constant of proportionality k. We're told that when t equals 0, the population is 300. So let's plug that in. 300 is equal to c times e. Well, being given t to the 0 is nice because we know that whatever k is, k times a t value of 0 will just become 0. So then this becomes 300 equals e to the 0 is 1. 1 times c is c. So I get a negative 900 is equal to c. So now our equation is n equals negative 900 e to the kt plus 1200. And we're told one more piece of information. We're told that n of 4 is equal to 600. So I'm going to solve this equation here. I'm going to solve 600 is equal to negative 900 e to the k times 4 plus 1200. Now we could solve this Without using an approximation, it would end up being something a little bit like yucky. It'll have natural log of something in it. So I am going to go ahead and just use a. Um, I'm just going to go ahead and use a graphing calculator here to just quickly solve this equation. So I will just graph negative 900 e to the, I'll call it 4x plus 1200, and I move that 600 over. So if I graph that, I should be able to find the intersection with the x-axis. So that gave me a k value of negative 0.101. You could do it by hand again. It would be a negative 600 divided by negative 900. So it's going to be a 2/3. So the natural log 2/3 divided by 4 is what that would be. And I'm going to type that in over here again, just to make sure that I'm not lying to you about that. Yeah, negative 1.013 even. All right, so now that we've got that equation, we've got the full equation. I'm running out of room here, but I'll say n equals negative 900 e to the negative 0.101 t plus 1200. We can now evaluate. We can say something like this. What is n of 8? So how many bears will there be in 8 years? Well, that's negative 900 times e to the negative 0.101 times 8 years plus 1200. And that looks to be about 798, and it says 0.826. So, I don't know if you can have 0.8 bears, but we'll say 798.826. All right, and lastly, it asks us to find the limit as t goes to infinity. Well, the limit as t goes to infinity, since it's e to a negative number times infinity, it's e to the negative infinity. E to the negative infinity is 1 over e to the infinity, which is 1 over infinity, which is 0. So this term here, I know it's kind of hard to read, it's all scrunched up. This term here, as t goes to infinity, must be going to 0. So this limit here is approaching 1200. And that's kind of the limiting, the carrying capacity of this system. That as we get closer and closer to that 1200, the bear population levels out. Okay, let's take a look at another problem. I think I'm going to scoot this one down first, though, because I am getting a little scrunched. All right. Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium, or the ambient temperature, right? So suppose a room is kept at a constant temperature of 60 degrees and an object cooled from 100 degrees to 90 degrees in 10 minutes. So it started at 100, 10 minutes later it's at 90. How much longer will it take for the temperature to decrease to 80? So the calculus is in Newton's law of cooling. It makes sense that Newton would have a law that needs calculus, what with him inventing it and all. States that the rate of change in temperature is proportional to the difference between the temperature of the object and the surrounding medium. Well, this is basically the exact same problem we just did. So I'm going to use y for the temp and t for the time in, looks like minutes. So the rate of change in temperature is dy dt. That is a constant because it's directly proportional to the difference between the object's temperature and the surrounding room. Well, the object's temperature is y, and the room temperature is 100. Is 60. 100 was the starting temperature of it. All right, so the temperature of the object is y minus 60. All right, let's solve this separable differential equation. You may be wondering why I did y minus 60 instead of 60 minus y. It's not going to make any difference how you do it. The only difference is going to be a slightly different probably a slightly different C value or something like that, but it's not gonna be different in the long run. It might be. What I mean by that is like we might have an intermediate step that's different, but we'll end up getting the right answer once we plug everything back in. All right, so let's just go ahead and integrate. If I integrate this, I think we know what this is. This is the natural log of the absolute value of y minus 60. And over here, this integrates to kt plus c. So when I exponentiate both sides, this becomes just y minus 60 equals ce to the kt. So y is equal to ce to the kt plus 60. All right. If we'd done 60 minus y, actually it would have been exactly the same thing because I would have added the 60, subtracted the 60, and divided by -1. So we all end up with the same value no matter how you do it. All right, well, we were told that it cooled from 100 to 90 in 10 minutes. So that means that when t equals 0, y equaled 100. That is nice to know because 100 then is equal to ce to the 0 plus 60. E to 0 is 1, so 100 is equal to c plus 60, so c is equal to 40. All right, we are getting closer and closer to that correct equation. 40 e to the kt plus 60. Now we just need to find k. We know it went down to 90 in 10 minutes, so the temperature was 90 10 minutes later. So 40e to the k times 10 plus 60. So again, that's going to be, I'll show a little bit more of the work here. 30 is equal to 40e to the k times 10. So 3/4 equals e to the, I'll call it 10k. Take a natural log of both sides, and you get the natural log of 3/4 equals 10k. So it's the natural log of 3/4 divided by 10. And I'm just going to get a decimal on that, just for our purposes here. But we could certainly express it that way. So we end up with k equals negative 0.0288, something like that. All right. So we have our final equation is y is equal to 40 e to the negative 0.0288 t plus 60. How much longer will it take it to decrease to 80? And that one, again, we could solve that algebraically. It wouldn't be terribly hard, but I'm just going to graph it. Where I'm letting x be my y value. And let's see if we can't get a nice looking thing here. All right, so I pulled this over here on the Desmos here. You can see it started at 100, and here's it decreasing, starting to level out though as it's getting closer to the ambient room temperature, which was, remember, 60 degrees. Well, we're looking for when does it reach 80. So I'll just graph and use an intersection tool here. And we can see that about 24.068 minutes. But it does ask how much longer will it take. So technically, it would be 14.068 more minutes after 10 minutes. I would want to make that clear that I caught that. I'm not, the total time is 24 minutes from when it started cooling. All right, I do have a couple of practice problems for you to work, so why don't you pause the video and try both of these, and then we'll go over them. All right, I hope you're ready to go over them. I'm going to go ahead and kind of move this down, though, for just a second, and maybe even move this one up just to give myself some more room here. There we go. The rate of change in the air pressure of a punctured tire is directly proportional to the pressure of the air still remaining in the tire. Suppose a tire with an air pressure of 40 pounds per square inch is punctured with a nail, and that 60 minutes later the tire is 35. what will the tire pressure be in 120 minutes? So the rate of change in air pressure, I'll call the air pressure y, and we'll be using y as a function of t. So dy dt is the rate of change in the air pressure. It is directly proportional to the amount of air still in the tire, which is simply ky. So I will separate my variables and integrate both sides. I get the natural log of the absolute value of y is equal to kt plus c. So then when I exponentiate both sides, I simply get y is equal to c e to the kt. Very common exponential function right there. We know that when t is equal to 0, y was equal to 40. That was our starting pressure before the puncture. So if you plug in 0 for t, you get e to the 0 is 1, so 40 is equal to c. So that c value is our starting amount in this situation. And we know that 60 minutes later it was at 35. So I can solve this. So I put 60 in for t, and then I'll just move it in front of the k. All right, so I get 35 over 40. What is that, like 7/8 is equal to e to the 60k. Take the natural log of both sides, and that's what we get there. And that I can get a decimal approximation on. To be negative 0.00 and then a bunch of 2's. And I'll round up to 3. So that's my k value. And now we can simply plug in for 120 for t, and we'll get the answer. And if we do that, we get (120 minutes), 30.609. PSI. All right. Okay, so let's go over some of these more of these practice problems. Practice 4.2. Did a quick costume change. Had to pause the video and do some work. So I'm back the next day to finish this off. Got new shirt on, in case you're wondering why that is. So hopefully I'm picking up pretty close to where I left off. I believe I got to go over practice 4.2. The rate of growth over time of the amount of bacteria in a petri dish is directly proportional to the amount of the bacteria in the dish. So the rate of growth, if I let y be the amount of bacteria over time, dt, is a direct proportion with the amount of bacteria y. So then we can use our separation of variable techniques, and we can separate these and integrate both sides. And I get the natural log of the absolute value of y is equal to kt plus c. Then when I exponentiate both sides, that gives me e equals c e to the y equals c e to the kt. When I bring that constant down in front, it allows me to take out the absolute value bars. All right, so we were told that at time 0 there were 200 units, so y equals 200 when t equals 0. Anything times 0, of course, being 0, and e to the 0 is 1, so 200 is equal to c times 1. All right, so now we know the equation is 200 e to the kt. We were told that at time 10 hours we have 400 units, so 400 is equal to 200 e to the k times 10. So if I divide both sides by 400, I'll get 2. Divide both sides by 200, I get 2 e to the 10k. Take the natural log of both sides, I get the natural log of 2 is equal to 10k. So the natural log of 2 over 10 is equal to k. And we can get a decimal on that, which is 0.069. We'll say 0.0693. So that is our expression in its final form. C was 200 e to the 0.0693 times t. All right, let's take a look at the next one. Practice 4.3. A cylindrical container holds a volume of water. A plug is removed from near the bottom, allowing the water to leak out. The rate of change of the height of the water in the container is directly proportional to the square root of the height of the water in the container. If at t equals 0 seconds, the height is 36 centimeters, and after 12 seconds, the height is 16 centimeters, write a function for the height of the water as a function of time. All right, so let's take a look at that. We know that it tells us the rate of change in the height of the water, so dH dt, is directly proportional to the square root of the height. So that gives me, when I separate my variables, this. And then if we integrate, this is h to the negative 1. So if I raise the power, it becomes h to the positive 1, and then I multiply by the reciprocal of the new exponent. Then that's kt plus c. So I'll make this h to the 1/2 is equal to, and if I multiply both sides, or if I divide both sides by 2, I still get kt plus c. All right. Now let's plug in some values at this moment. When the height is 36, when the t is 0. So 36 to the 1/2 power is equal to c. So 6 equals c. We're also told that after 12 seconds, the height is 16. So 16 to the 1/2 power must be equal to, we're putting in, let's see here, 12 for t. So k times 12 plus 6. So 4 is equal to 12k plus 6. So I get a negative 1/6 is equal to k. So we get h to the 1/2 is equal to negative 1/6 k. Oh, that was my k. Sorry, negative 1/6 t plus 6. And to get h as a function of t, I will square both sides. But in reality, we should limit our domain that once t is equal to 0. Once h is equal to 0, we don't want t to continue, because it would actually, this function would say it starts coming back up. But we'll just leave it like that for now, because our next question actually asks us to find after how many seconds is the container empty. So I'll just set the height equal to 0. And so square root of 0 is 0. And let's see here, that gives me, I believe that is a negative 36. Or just a positive 36, actually. Sorry, 36 is equal to t. So 36 seconds. All right. Next question. The rate of change in an athlete's 400-meter race time, t, is directly proportional to 49 minus, it says minus w. That should be minus t. That's a typo. All right. Where w is the weeks of training and t is the completion time in seconds. A, if the athlete ran a 400-meter race in 64 seconds at the beginning of the training season and ran 60-second 400-meter race after 10 weeks of training, write a function for t of w. So the rate of change in the time to complete the race per week, so the rate of change over the number of weeks of training, dt dw, is equal to k times 49 minus t. So dt over 49 minus t is equal to k dw. And then we can integrate this. And technically, if you do use substitution, the left-hand side of this actually integrates to negative the natural log of the absolute value of 49 minus t. And that gives me kt plus c. But because of the k and the c absorbing the negative, I can actually just ignore it because when I divide it out, it goes away. And we end up with 49 minus t when we exponentiate both sides equals c e to the kt. And solving for t will give me c e to the kt plus 49. It was taking 64 seconds to run the race when w was equal to 0. Oh, I got t. I'm sorry, I forgot. See, I didn't want to use capital T and lowercase t, so I ended up using w since we're measuring time in weeks, and I still did it. I hope that didn't confuse you too much. W, we're doing, because this is dw, the integral of k dw is kw plus c. There we go. So we know that when w was 0, we were getting 64 for our time. So 64 is equal to, if w is 0, that becomes e to 0 is 1, so it's just c plus 49. So c is equal to 15. We also know that after 10 weeks of training, we were running it in 60 seconds. So that's 60. Let me borrow some room here. Just slide that down. So we know that 60 is what we have when w is equal to 10. So 15 is my c, e to the 10 times k plus 49. Subtracting 49 gives me 11 is equal to 15 e to the 10k. And so you're going to end up with the natural log of 11 over 15 divided by 10 for your k value. And I can do just a quick calculation on that. That's a negative 0.0310. So our final equation for a function, time, to run the 400-meter dash as a function of weeks spent intensively training for this particular athlete is 15e to the negative 0.0310w plus 49. The next question asks, if the athlete continues to train indefinitely, what value does the race time approach? Well, that means we're going to be taking a limit as w approaches infinity. And if I do that, I get 15 e to the negative infinity plus 49. So that's 15 over e to the infinity. E to some negative exponent is always going to 0. So that's 0 plus 49. So we're going to be approaching 49 seconds. So that seems to be the limit what this athlete can achieve no matter how long they train. If we get some sort of significant change in the situation, they change that limiting factor of 49. Maybe like a new technology, new training staff, something like that could really change it. All right, so I think that was our last question. I hope you enjoyed that, and I'll see you in the next unit.